Welcome back everyone. So in this video, we're going to look at exponential growth and decay. As you can recall from last video that we have discussed, we discussed the natural logarithm. So we discussed something related to y equal to e to the power x, as you can recall, and that leads to x equals to log ey, and then log e means ln, and it's just lny. And now this will play a huge part of today's concept. So at this point, what I want you to do is, if you haven't read your reading, pause this video, go back, read exponential growth in details for 10-15 minutes or whatever time you need, and then come back to this video. So if you click on this is going to take you to a math space page, and there you have all the related reading you need. So I'll try to explain the concept in a nutshell, and then we'll go ahead and solve a problem, because I think solving problem for this particular concept is the best way to teach. So if you think of a certain population, let's think of a certain population, or let's say population in Australia, okay? Population in Australia is currently, let's say in 2021, is P naught, and the scientists can make a model that, like, how the population is going to look in 2040. How do they do that? So they use this method, or some population, let's say some birds or some animals are going to be extinct, and they're reducing every year by a certain number. So how long do we have before it all disappears? So these are the questions that you can solve through these exponential growth or exponential decay equations. So the equation is P equals to P naught uh, e to the power kt. Remember that guy, e? That's coming back here. So this is natural logarithm. So what are the other things? This is the population at a particular time, so we can call it P of t. This is population at the beginning, or we can call it initial population. This doesn't necessarily need to be people, it can be anything. It can be birds, it can be animals, it can be dogs, it can be cows, anything at all. E to the power kt, where k is the constant. Now that constant plays a significant part whether the population is decreasing, population is increasing, how rapidly it is increasing, and whatnot. So if it's negative, it's decreasing clearly. If it's positive, it's increasing. And t is the time. So that's everything you need to know about the formula. So how does that play out in real life? We'll go through an example. Let's get straight to it. So think of this problem, okay? So Niger's population's T years after the year 2000 is modeled by this. So you already are given with the model. So as you can straight away see, when it's in 2000, so we are starting the model at 2000. So the 2000 number of population was 17.7 million. Because remember, P equals to P naught e to the power kt. So this is our modeling. So this is our P naught, this is our constant. So if you can compare with that, this would be your initial population. And this is P is population at a certain time after 2000. Now, state the continuous growth rate used in this model. So that's the growth rate, the constant 0.0078, that's the growth rate. So if we can head to the problem straight away, let's look at this. So the year 2000 corresponds to t equals to 0, and the value is p at t equal to 0 is simply whatever you are going to get out of this equation. So in other words, if you put t equals to 0, e to the power 0, e to the power 0 meaning 1, anything to the power 0 equals to 1, remember? So it's 17.7 million. That's the initial population. That's something we also got straight by comparing with the model. Now, exponential function is p equals to a e to the power kx or a e to the power kt. So the growth rate is the k, which is 0.078. Now, next question says 2005, what would be the population? Simply, what does 2005 means in terms of year? 2005 minus 2000 is 5 years. So in 5 years, what would be the population? That's the question. So you just simply put in P of 5. So in other words, we are looking for P of 5. So P of 5 is simply putting 7.7 e to the power 0.0078 to the power uh, uh, multiplied with 5, sorry. And then whatever you get, that's the population that should be in 2005. So in this way, you can model 2050 as well, given your modeling is good. So that's why the modeling needs to be perfect. In other words, from previous data, you can find out what your k needs to be. So sometime you will see you'll be given the population, you'll be given the number of years, you're supposed to find k first, and then go on with the concept. Now this time, oh sorry, this time we want to find out, okay, t, and we are given with certain population, in other words 22 million. So when do we get to have 22 million people? Simply we just using our logarithmic skills we can find out our t, remember? So p equals to p naught e to the power kt. So we have everything. So we have, this is 22 million, this is 17.7 million, e to the power, we also have 0.078t. So only thing unknown is t. But as you recall from logarithmic class, you can simply write this as that, and 7, 8, I think that should not be a minus, that should be a dot. And if you can compare this is simply y equal to e to the power x. But these are, crazy numbers, looks like the numbers are not nice. But you can see this is similar to something like that, which we already know how to handle. So this would be 0.00078t equals to, remember E is ln, so ln 22 17.7. So you can get this number from the calculator and divide that by 0078, you will get your number of years. And that's what been done here as well. So you can see from here you can find your t. So turns out t is 27.9 years. Now the next question could be, something else completely, uh, maybe give you a particular time and then ask you to find out population in that year, which was the first part, then ask you to find time as well. And then if you look at number E, E is asking Niger's population t equals to 0 was 17.7. We want to find the value of t when p doubled. So this time we are trying to find population, how long it takes for the population to double. This is the exact same problem that we solved before, but the only difference is earlier we solved for 22 million. Now we are solving for double the population. That's all. In other words, p naught e to the power kt we can say P over P naught e to the power kt. This thing is double. In other words, this thing should be 2. 2 equals to e to the power kt. We already know our k. We already know t. So simply kt should be equals to ln 2. And you can get ln 2 from the calculator. Divide by the k. In other words, k is 0.0078. You can find out the time to double the population. In the next coming videos, we'll also learn about half-lives. Since this video has already been more than 10 minutes, so I don't want to add new concepts to it. Maybe in the next video, we talk about half-life and we talk about other important applications related to natural logarithm. So now what you should do is go through a few more problems, try to solve the problems. There are solved problems in the tutorial. You can have a look and try to solve it yourself first before you proceed to the next video. And of course, there are questions here as well for you to practice. So if you can click on questions, you'll have plenty of problems to work with. Go through them. If you need help, click on the video. The video will take you step by step. If you're still struggling, just send me a message on WeChat, and then we can sort out uh, sort out an appointment, and then we can go through it together if you're still struggling. And I will see you guys in the next video. Thank you.